Hello! Welcome to some more chemistry. I'm Dave Hicks. Today we're going to talk about ionic dissociations. Ionic dissociations, at the end of today, you should be able to define what we mean by that word dissociate. And we should be able to find ionic compounds and to be able to just understand what it means for them to dissociate, why they dissociate, what types of compounds dissociate. And then finally, we're going to use chemical equations to kind of represent this dissociation of ionic compounds, and then we'll be able to use those later on in our chemistry experiences. So dissociation, the word dissociate means to break apart. Association is to come together. Dissociation means break apart. And ions can do this when they're dissolved in water, ionic compounds. And the reason ionic compounds can do this is because anything that's an ion, if you remember back when we talked about ions, or if you haven't watched that video yet, you might go back and see why ionic particles, why they are ions, how they get their charges, and what's going on with their valence electrons. But remember that the valence electrons, they wanted to have 8, an octet of valence electrons. And these ions have those 8 electrons in their valence level because they've either given away electrons or they've taken electrons away from another atom. And when they did that, they have their own full octet set of electrons. And once that transfer was made, they are now separate entities, free to go. They have the correct number of electrons, and they don't need to bond with anything in order to be stable in itself. So they're free to depart from one another. Now they stick to each other, positives and negatives stick to each other because of electrostatic attractions. Positive, negative stick, right? You've been told opposites attract. That's where we get that from. And so ionic compounds, when they are a solid, they're stuck together because of this positive-negative attraction. But there isn't any type of a bond that is forcing those two things to actually stay with each other. So when they're put inside of a medium like water, they are actually able to detach from one another and go about their merry way. Now here I have some magnesium chloride. And this magnesium chloride, I'm using the black here to represent the magnesiums and the green to represent the chlorines. This is how it normally looks as a solid. We have it in some type of a crystal lattice arrangement, right? Positive, negative, positive, negative. And that's how it's stuck together with that electrostatic attraction. But when I put it into water, then the magnesiums and the chlorines, they can dissociate or break apart from each other. And I'm showing you here how they're just able to come apart and break apart into their own individual ions, float around in solution all on their own. I won't do all of them there. There's enough of them for me, I think. Now, when they break apart and they float around in solution, they disperse equally, and they get surrounded by water molecules, as I'll show you in just a minute. But when they do dissociate like that, it breaks up into the two ions, the magnesium ion and the chloride ion. Magnesium here will write Mg, and if you look on a table that has the charges, you'll see that magnesium has a +2 charge. So that's what we would write for it there, magnesium with its +2 charge. And what else it breaks up into are chloride ions. And chloride has a -1. Again, I recommend looking on a periodic table to see the chloride ion and to get what its charge is. Now, one thing you might be asking yourself is, what about this 2 down here? I don't see it over there. Well, the chloride ion is not diatomic. It does not need 2 chlorines to be stuck together in order to have 8 electrons. They're free to go. So, but we still have to keep things balanced, don't we? So I may not need 2 chlorines stuck together like this. The chloride ion is free. It's a single unit. It's able to go off all by itself. But I still have to keep things in balance. So if I have 2 chlorines over here, I'm going to need 2 on this side, only I'm not going to write it there. I'm going to make it a coefficient out front. Now this comes to the symbology of some of these numbers that we use, right? You know, sometimes we put a number there, sometimes we put numbers here, sometimes we put numbers as coefficients. Well, when we use a number that's a subscript like that, we're referring to those things being stuck together. You know, that becomes one single unit. And in fact, we call this a formula unit of magnesium chloride. We're referring to them as all being stuck together. But when we put the number as a coefficient out front, it represents 2 independent units of whatever it is that that coefficient is front of. In this case, the chloride ions. So the 2 that is a coefficient represents 2 separate entities. The 2 that's part of this and magnesium chloride that's subscripted, that means 2 of those, but they're not separate. It means it's all part of some unit or some cluster of atoms that's stuck together. So symbology and where we put those numbers, where the number is located, is very important to us in chemistry. So keep an eye on that. All right, I want to show you what this looks like in water. So in water, it might look like this. Here I have my chloride ions and my magnesium ions floating around, and you can see the water molecules all separating them in between. On a separate video that I did, I talked about the water molecule, and it is what we call polar, meaning that it has a little bit of a negative end, a little bit of a positive end. It's kind of like a magnet. So this magnetic attraction, the positive end is where the hydrogens are, and see how they're surrounding, the red hydrogen ion atoms here are surrounding the negative chloride ions. And the oxygens are a little bit negative on the water molecule, and you can see how they're surrounding the positive magnesium ion in the center. And that's sort of what happens is the negative ends of the water will actually dissociate or break apart these pieces that's part of this crystal lattice. And the attraction then between the ions and the water become the attraction that holds that solute into solution. All right, so what about polyatomic ions? Well, I recommend to students that they look up the ions on their ion chart. And because there are only 2 ions as part of an ionic compound. There's a cation and there's an anion. The cation is usually a single element, that is a metal that is should be located in your cations chart. And then whatever is left over is the anion. Now sometimes that anion is a polyatomic anion. And those things many times will have an oxygen in them, as is in the case of these 2 examples over here. So here I have some sodium sulfate, and Na2SO4 is our sodium sulfate. And here I have my crystal lattice of it. I got the gray atoms being the sodium and these clusters of atoms back here being the sulfates. So when it dissociates, you're going to see these sodium atoms are going to break away and go into solution. And along with that, the sulfate cluster is also, this is the polyatomic ion. Look how it has the sulfur surrounded by the 4 oxygens. So this sulfate ion, it stays together. The sulfurs and the oxygens are covalently bonded. They are sharing electrons between them. But somewhere in there they have a couple extra electrons giving them a charge. And so the oxygens and the sulfurs are all going to stay together. However, they themselves have a charge and will bond ionically. So this substance will break apart, and for every 2 of these sodium atoms that go into solution, 1 of these sulfate ions is also going to go into solution here like this. All right. Now, to represent this, I'm looking up my ions. I know that sodium here, it has a +1 charge. And then over here, I have a sulfate ion, and I'm going to write that as SO4 with a 2 minus. Now notice the 2 here for the sodium. That means that there's 2 of them. I had a student say to me the other day that, hey, this is kind of like taking it apart. He remembered back when we put these together as 2 sodiums and a sulfate, and we put it together to create this formula. We called that crisscrossing the formulas so that we could get the correct ionic formula. And he said, this is just kind of undoing that, isn't it? It's just breaking it back apart. And I said to him, yep, that's exactly what's going on here. So here now I have 2 sodiums. I need the 2 positives to go along with this 2 negative, right? But you might be asking yourself, hey, there's a 4 here, but I didn't put a coefficient of 4 over here. And that's right, because again, remember this 4 here means that it's part of some cluster. It's bonded together in some way. And as you can see, each of these sulfates is bonded to 4 oxygens. So the 4 is not going to come out front out here. That 4 is going to stay there, showing that there are 4 oxygens that are stuck to this sulfur right there. And each one of these is just 1 unit. So I have 1 independent unit of this sulfur and 4 oxygens, this sulfate. Again, just to stress, I always tell my students, go look it up on the ion chart, write it down exactly the way that it looks on that ion chart. If you look on the ion chart, you're going to see SO4, and you'll see it with a -2 charge. Write that down exactly the way it looks. Don't try to reorganize it. If I were doing that for sodium, it would just be Na with a plus. And you can see, hey, there's 2 sodiums here, so I'm going to need to put 2 sodiums, a coefficient of 2, to show that those are 2 independent units right there. All right, let's try this one more time with the aluminum nitrate down here. The gray is representing the aluminum. These green-blue clusters here are the nitrates. And so when this gets put into water, it's going to dissociate. Again, they each have their own octet of electrons. They don't need to be bonded. They can break apart into individual units. And that is what happens. So here I'm showing that the aluminums can separate themselves entirely from the nitrates. Here, I'll leave one of those back there, I guess. And again, now writing the formula for this, the balanced equation, I would look up aluminum, and I'm going to see that aluminum has a +3 charge. So I'm going to write it with its +3 charge. There's only one of them there. I don't see any subscripts down here. So I can see there's just one aluminum. And then, oh, look at over here. Here's our nitrate, the NO3. If you look that up on the ions chart, you'll see it's NO3 with a -1. Again, write it down exactly the way that it's written on there. And then I see this parentheses and a 3 over there. If you remember when we were doing ionic formulas, if you needed more than one polyatomic ion, you'd put it in parentheses and then put the subscript outside of that. So here I have 3 nitrate ions, and so I need to represent this with 3, the coefficient of 3 out in front, because there are 3 individual ions that are free to separate themselves and go on their merry way. Okay, so we've seen how things dissociate, break apart, and we've kind of modeled that with these circles on my magic board, huh? And we've also seen how to kind of represent this with balanced equations here, if you will. And let's try some more, maybe without the models, huh? So here's what I'd like you to do. I'm going to do the first one up here, the calcium fluoride for us, and then I'm going to give you a chance to try it with those other 3 down there. What I want you to do is I want you to show this in its dissociated form. So if this were to break apart and dissociate, what would it look like? Again, look things up on that ions chart. See what their charges are. Very important that we show their charges. And write them down exactly the way they look on there. In this case, the fluoride ion is just going to be F with a minus. There's two of them. Yes, I know. And they're two independent ones, so that coefficient of 2 is going to go out there, right? Okay, I'm going to give you a chance to do these three. Press that pause button. Dissociate those ions. I'm going to be right here when you get back with the answers so you can check to see how well you're doing. Okay, how did you do? I bet you did all right with this. So here's my answers. You can check things over, make sure you got the right coefficients in the right place. Some of the issues that may have arisen during this, let's take the lead nitrate over here, is to try to figure out which charge would the lead be. Well, lead has more than one charge. It could be +2 or it could be +4. Maybe you saw that on your ion chart and had that question. How do I know which charge it is, +2 or +4? Well, that we have to go to the anion, right? And since I had two nitrates with their negative charges, we know that this bonds together so that the charge cancels. We have to have the same number of positives as negatives. And since I have two negatives over here, this lead must be a +2 charge to cancel out the two negatives of the nitrate. For the potassium carbonate, hopefully you got that one, similar to an example I just did before. And finally down here, this is the tough one. I threw this in as the challenge. Here I've got ammonium, and many times people don't see this one very much. It's the only cation that I know of that is a polyatomic ion, at least a common cation. It's a positive ion. And there were two of them. See how you got the parentheses in 2? So there's my 2 as my coefficient for those ammonium ions. And then there was the sulfate. All right, so today we saw what dissociation was. We saw some models about how it breaks apart, what types of particles stay together. We learned about the subscripts meaning versus the coefficients meaning. A lot of information there today. And finally, we saw how to show this as a balanced chemical equation of some type. And I guess that's all for me today. Good luck with your chemistry, and we'll see you next time.